In this video, we're building on the derivation we made for the response of a system to exponential inputs. In the past couple videos, we were focusing on the step response, which is when the input is an exponential input, but it is with s is equal to 0. And so now here we're going to talk about frequency response. And so that is specifically sinusoidal inputs and the response due to sinusoidal inputs. And so that is the special case again for exponential inputs where s is equal to plus or minus I omega, so purely imaginary inputs. And so in that context, we look again at this division that we derived before and also used in the step response, where we talked about the transient response and the steady state response. And again, using the same notion that if A is stable, this transient behavior will decay away because of that exponential AT, e to the AT. So that will go away over time, and what will be left is this piece here. And so what's interesting is that so this might be some complex number, especially if s is imaginary. So this value right here will be some complex number, and we'll represent it in terms of its magnitude and its phase. So instead of a plus ib, we'll represent it in polar form. And then we'll also have this exponential that's on the back end here. And so if we write this bracketed term in this polar form, this allows us to combine the exponent terms. So we have the magnitude, and then we have st plus I theta. And so in the case where s is this purely imaginary value, so when it's positive, then s becomes I omega, and then we get a term that looks like this. If it's negative I omega, then we get a term that looks like this. And so that means that the steady state solution is looks like these solutions. And if you recall, these are purely sinusoidal outputs. And so the key thing here is that the sinusoid is going to have a frequency omega and then a phase given by theta. And so what's interesting here is the key idea is the fact that the input is a sinusoid with frequency omega, and the output, the steady state output, is also a signal with frequency, a sinusoid with frequency omega. So the steady state response is the same frequency as the input, and so that's the particular piece of magic that happens in terms of frequency response. So just kind of pictorially, what that means is that we inject a sinusoidal signal with some frequency. After some amount of transients, you get down to the steady state behavior where now you have this oscillation, this pure oscillation. And the key thing is that the frequency of this oscillation is the same as the input. So what's interesting to characterize, though, is the fact that there could be shifts in the amplitude value. So in this particular case, we can even see that this maybe has amplitude of about maybe about a half, maybe a little less than a half. Whereas here in this graph, the amplitude oscillation is much, much smaller. So that's fractions much smaller than before. So the amplitude could change, and that's given by this m factor right here. And there can also be a phase shift, which is given by this theta. And so we'll look at that in the next slide. So kind of going back to sinusoidal notation, if we have a sinusoid with input amplitude a sub u and some shift phi u, then if our output, we know it has the same frequency, so that means omega is going to be the same thing, but we could have different magnitude and different phase. And so because of that, the signals would look something like this, where the blue dashed line is the input and the green solid line is the output. And so there could be differences in these amplitude heights. And then the crossing, so we talk about a phase shift. The way that you can look at that is either where these things cross 0 or where they reach their peak. So that value is always going to be shifted by the same amount if these are constants. And so if we quantify that, we can kind of think about that delay, or it could be an advance, as a delta t. So in this case, this diagram is saying that capital T is the period, and then this is the fraction of the period that it is delayed or advanced. So what we can do is then we can define the magnitude, or the gain, which is the difference in the not difference, but the division of these, the ratio of these magnitudes, the ratio of the output over the ratio of the input. So if it gets smaller, this is going to be a fraction. If it gets amplified, then this will be a value bigger than 1. And then the phase is the difference between the output and the input. So if it's an advance, that means it's this phase lead. So it means the output is somehow ahead of the input, and the phase lag means that it's lagging behind. And so this is already something you've kind of explored through Lab 2, but the key idea here is the fact that at different, what's really important here is that this omega value is not just located inside this frequency, but it's also under the hood inside this magnitude and this phase. And so the magnitude and phase is not just a constant across any choice of frequency, but if this input were to change frequency, the magnitude and phase would also change. And if you look back on the previous slide, that capital M and the theta terms that we had in the previous slide, those were actually functions of the frequency omega. And so what becomes interesting is then across different frequency values, so this is for different frequency values, you can have a specific choice of phase and of gain. And so what what frequency response is really talking about is it's talking about the magnitude and phase across all the different frequencies. And so what we'll be doing is then looking at how do we read a plot that looks like this, which is called a Bode plot, which summarizes all frequencies, where essentially this particular phase lead or phase lag and this particular magnitude gets plotted as a single point on this curve. And so our goal will be to be able to read these and be able to construct these from transfer functions so that we become more versatile at understanding how the frequency response is captured and quantified for these different systems. Now we'll take a look at how you derive the frequency response from the Laplace transform approach, now that we've done that through state space. It's worth stepping back just for a minute and thinking about why frequency response is useful. Step response seems to be a natural choice in the sense that there's many systems where you might turn on an input and leave it on at a constant value. Frequency response is important because it represents a lot of the disturbances that we have in systems. So typically we don't drive our systems with sinusoids, although that's not always true. There could certainly be some examples where you do. But for example, the noise characteristics that represent essentially disturbances that may impact a system. You could imagine like a wind that's buffeting against a plane or a vehicle or some other system, or some sort of vibration that's being applied to some system. So there's a number of different ways in which that frequency response is important in understanding the environmental conditions of control systems and how it impacts their operation. One of the other important things is the fact that the frequency omega is equal to 0 is also contained within that frequency response. And so that step response, we'll see ways of connecting the step response back to the frequency response because it's a special case of the overall frequency response as well. So from a Laplace point of view, if we have this input-output characterization where the system is really modeled by the transfer function g, and our input is some sinusoid, so in this case I'm just going to take the sine function, then in that case our Laplace transform of that sine function is just given by this quadratic in the denominator. And when we put that all together, we get our overall transfer function for y. If we were to then want to apply our whole methodology where we break this into partial fractions and then take the inverse Laplace transform, the next step would be to calculate the partial fractions. And so whatever the poles of G are, we would split those into their various terms, and then we would also have a term, because we have this in the denominator, we'd also have terms that coincided with the two poles that are associated with the sinusoid. So when you do the cover-up method to calculate these coefficients that are for the poles of the input, then you essentially are evaluating G of S and one of the poles at either minus I omega or I omega. And what that ends up yielding is the transfer function of the original system, G, evaluated at minus I omega, and then a quantity that's like A, which is the original amplitude, A, divided by minus 2I, and then similar for the other value, the positive value. So what that ends up meaning is that when you do the inverse Laplace transform now and get it back to the time domain, the poles of G of S, all of these terms, correspond to all these exponential terms here. And if the original system is stable, like what we assumed in the state space case, that all of these terms have poles so that these exponentials go to 0. So they don't all have to be real, they could have complex parts, but that overall the real parts are all negative, and so that means that all these exponentials decay away to 0. So that means what we're left with is just this bit, and this bit is really exactly just a sinusoidal output, and so we'll reformulate it in the next slide to make that a little bit more clear. So again, we've indicated that these are all going to decay away to 0 because it's a stable system, and we're left with these two pieces. And if you look at these denominators and these exponential terms, you'll see that we can rewrite that in terms of a sinusoid. And that depending on the magnitude and the phase, essentially this G of minus I omega and G of I omega, these factor into the magnitude part of that and the phase part of that. So again, essentially you're going to rewrite these terms in terms of their magnitudes and their magnitudes and phases, essentially in polar form, because these are going to be complex values. So you're going to write those in polar form. The magnitude comes here, and the phase part comes here. And what we get then is that the steady state value of the output is a sinusoid at the same frequency as the input. So that's exactly what we discovered from the state space point of view, and that it's scaled by some amount that's driven by the magnitude of the transfer function G evaluated at omega. And similarly, the phase is then the complex phase of the transfer function evaluated at I omega. And so this represents the shift, and this represents the magnitude change, which gives us a little bit better clarity than what we got with a state space perspective on how the value of omega parameterizes the different magnitudes and phases you would get over different values of frequency. And so what we're going to be doing now is studying how to look at those Bode plots and how to interpret them in terms of the system behaviors based on their frequency response.